In this slidecast, we're going to talk about using abstraction to manage complexity. Now, abstraction is a powerful technique that can help you as the programmer deal with complexity. Abstraction is a simplified model of a physical entity or activity. Here's an example. You've used variables as you've written programs, and a variable has a name and it denotes a storage location in memory for some value. And you don't need to concern yourself with the details of how the computer physically represents memory or how the bits of this data value are stored. You can just refer to the variable name and think of the value that's associated with it. We use abstraction all the time in the real world. So to drive a car, we need to know a couple of basic pieces of information. We need to understand how we can use the key to start the engine. And if we can understand the accelerator and the brake pedals for controlling speed and the steering wheel to control direction, that gives us most of what we need to be able to drive. Now, you don't need to know all the details of the car's electrical system, the braking system, or the underlying steering mechanism. And that makes it very nice because we can drive and we can ignore a significant amount of complexity. So now this past summer, I went back to England where I served my mission, and I rented a car and drove on the other side of the road for about 10 days. And so there's more to driving than just these three things, as I understood very clearly. Unfortunately, I made it back alive. Okay, procedural abstraction is the idea that when we develop procedures or functions, we can separate our concerns about what the function must do from how the function will do it. So when we specify what we expect from a function, we can just think about what it's doing and not the details of how it's going to do that. And we can use that high-level abstract specification to design a solution before we even know how we're going to implement it. So let me give you a real-world example. When I was scheduling my time for the summer and I knew I was going to return to England, I could come along and say, well, from this week in July, I know I'm traveling to England. So I knew what I was going to do with my schedule, and then I could do all other kinds of scheduling to avoid scheduling other events here because I know I would be out of the country. And I could plan that well in advance, even though I delayed for quite some time before I actually figured out the details of how I'm going to get to England and how I'm going to spend my time while I'm there. So we do these various levels of abstractions all the time in our lives. And we do that same idea when we write programs. So here we have a function, retrieve and display an entry. So we're back to our telephone directory example that we've been talking about. And at level 1, here's a function, and we can break it into a series of subproblems or functions that it will take to achieve the higher level abstraction. So level 1 is this high-level abstraction to retrieve and display an entry. And level 2 is the more detailed steps that we need to accomplish that higher-level goal. So we could read a name from the user, find the name in a directory, get the directory entry information, and then display an entry to a user. Now, once we've defined these lower level functions, if we just know what they're going to do, then we can write this program. Here's a snippet from some program where we want to read the name, and so we can call this function readName. And we understand that readName is going to return probably a string that's a name. And since we know what it's going to do, we can invoke this function even if the details of that function haven't actually been created. And this other example, directory.getName, this gets a number associated with the name that's passed in as a parameter. So here are two examples of a function, and once we've created, using our procedural abstraction, we can use these functions when we design this routine, even if the details of those functions haven't been created. Data abstraction is concerned with the data objects for a problem and the operations that we perform on those data objects. We don't have to be overly concerned with how they're going to be represented or stored in memory. This gives us a logical view of that data object as opposed to a physical view which is concerned about the internal details of how we would represent that data in memory. Once we understand the logical view, then we can use the data object and its operators in our programs. Someone else might have to eventually implement that data object and operators before we could actually run a working program, but I can make use of this as I design and develop other associated functions. Now in C++, we call these operators member functions. We can use those terms interchangeably. The C++ string class illustrates data abstraction. We can use string objects and their operators, such as length and at, without knowing the details of how it's implemented and not even caring about the details like the sequence of characters stored in memory. So both procedural abstraction and data abstraction enable designers to make implementation decisions in a piecemeal fashion. So we can postpone decisions regarding actual internal representation of data objects and the implementations of the operators, and we can start out with just the abstraction in terms of what an object, what it does, and not how it does it. And this is very helpful for you to be able to break up your programs into manageable pieces, and it really helps us manage complexity on a large software project that involves many, many people. So you can control this complexity by separating top-level design from lower-level implementation details. Now, if the details of an implementation are hidden from the higher-level module, a C++ class, the higher-level class can access the data object only through its member functions. So if we make private fields in our C++ class, we can only access those fields from the member functions of that class. And this is an advantage because when we have to make internal changes to a function, we don't have to rewrite all the higher level class or all of the other programs that make use of that class. And this hiding process is called information hiding. And it's a real key aspect of developing software, because in many cases it isolates changes. There are times when we make such a fundamental change that it has a rippling effect, but we'd like to make that as rare as possible. Now here's an example using the phone directory. If I started out with my entry, which is an object, and if we had a field, a data field called name, and we made it public, let's assume it was a string, then when other people go to use our class, they could access that public field, and they could access it by specifying myEntry.name. Now suppose later on we decide to change the internal representation, and for the sake of an example, suppose we were going to change name from a string to instead have an array where we hold both the name and number, and this will be an array of strings, and the names will be at position 0 in the array. So now everywhere we had previously in other functions referred to myEntry.name, we now have to update it to say myEntry.name sub 0 to reference that first index. 0 is indexes into the first position in the array. So if this is a public field and many other programmers had made use of that, then this could be an extensive change. What would have been better is to use the principle of information hiding and make that field private and have a getter method called getName, where other people would call getName to get the string name. If we had done this, then we could make that internal representation and change to an array, and that change would have been isolated in the phone directory class. So again, if we made a fundamental change so that names no longer return strings, then that would have a broader impact. But we can get maybe some significant improvement by isolating changes when possible. And that brings us to the end of this slidecast.